Hello everybody, welcome to the next video. In this video we'll be talking about rotation and rotational symmetry. So much like the last video where we were talking about linear symmetry and reflections, rotational symmetry is another way of manipulating a shape to make it look the same. So much like with our linear symmetry or our reflections, what we do is we take a shape and we reflect it, right? And we can look at how we reflected about certain lines. But what happens is there is a certain looking the same as the old shape, right? Well, the same is true for these rotational symmetries. So for example, if I look at these three pictures here, we have rims from a car. What happens is this top part here, right, as my car moves forward and the rim starts to turn, it'll get to this piece right here. Right, so when it's turned that much, what you'll notice is that the shape itself actually doesn't look any different than what it did originally, right? So again, this idea of looking the same in math we call symmetry, right? So what is rotational symmetry? So a shape can have rotational symmetry when it's able to do that, when you're able to rotate it and have it look the same as it did originally, without needing to rotate it one full rotation. So with that previous example, if I'm looking at my rims on the car, right, it doesn't have to go all the way around to look the same. It'll look the same when it spins just a little bit, right? And then it'll look the same again when it spins just a little bit more, and then a little bit more, and then a little bit more. And then finally, it will get back to where it started and it'll look the same because that's where its original position. But it does so multiple times on its way through one full rotation. So a shape will have rotational symmetry when it coincides or it matches with itself in a rotation that is less than 360 degrees. So again, 360 degrees being one full rotation. A shape that only matches itself after that one full rotation, it doesn't have rotational symmetry. There is no rotational symmetry because it never looks the same until it gets back to where it started. But a shape that does match itself at least 2 times in that rotation does have rotational symmetry. So for example, if we look at these shapes down here, this little kind of cross shape, the starting position, we have our little red dot at the top here. And then what happens is when we rotate this shape 90 degrees, so when this red dot goes from the top to the right, we end up with a shape that looks exactly the same as it did originally, right? And then when it rotates another 90 degrees, we're down at the bottom. And again, the shape looks the same. And then when it rotates another 90 degrees, we're on the left. And again, the shape looks the same. And then finally to rotate another 90 degrees and get back up to the top, and we'll be where we started, right? So we take a total of 4 rotations of 90 degrees to find this shape back to where it started. And each of those 90-degree rotations, it looks the same as it did originally. Now, something interesting that happens here, if I take those 90-degree rotations, so 90 plus 90 plus 90 plus 90, I end up getting my 360 degrees, right? Because that's what it took to go back to where we started. So because it takes 4 of these steps of 90, right? 1, 2, 3, 4 of them to get me back to where I started, we would say that this shape has a rotational symmetry order, right? Order of 4. And more so, not only that, but we could actually talk about the angle rotational symmetry as well. So for example, if I know the order, if I know it's going to take 1, 2, 3, 4 steps for it to get back and 4 times it's going to look the same, right? Then what that means is I can take my full circle, my 360, and I can divide it by 4 to figure out what we call the angle of rotational symmetry, right? So if we think about it, so order is number of partial, right? Not full rotations, but partial rotations, right? To get back to where we started. Degree is the size of each partial rotation, right? It's how much do we have to rotate in order to get back where we started, right? And if a full rotation is 360, right, that's one full circle is 360 degrees, right? Then to find that degree, to find that size, what we're doing is we're taking that 360 and we're dividing it by the number of partial rotations we had to make, or in other words, we're dividing it by the order. So for that previous example, right, if I wanted to find that 90 degrees we were talking about, if I didn't already know it was 90 degrees, what I would do is I would take my 360 and I would divide it by my order, which is 4, and we can see that that is in fact going to be 90. Okay, so if we're thinking about kind of the previous video and now this new information, and we're talking about different types of symmetry, well, let's look at the following shapes and see if we can't figure out what types of symmetry are involved. So for this first shape here, do we have any linear symmetry? Yeah, we do, right? We have a triangle. It looks like it's an equilateral triangle, which means there's 3 equal sides and 3 equal angles. So if I were to take this triangle and cut it in half, there's my first linear symmetry, my first line of symmetry. There's another one there. And then finally, there's a third one right here, right? So we would say that this has 3 lines of symmetry, right? Great. What about the order of rotational symmetry then? Right, so what is the rotational symmetry of this shape, or in how many ways can I partially turn this shape to make it look the same as it did previously before getting back to where I started, right? So again, this is a triangle, right? So what happens is when this corner right here rotates until it gets down to this corner here, well, there's one partial rotation, and when that happens, it'll end up looking the same as it did originally, and then it will continue rotating until it gets here, and that's 2 partial rotations. Again, it'll look the same, and then finally, it'll rotate one more time for a 3rd partial rotation before getting back to where it started. So the order of rotational symmetry here is 3. And then that means that the angle of rotational symmetry, again, if I take those 3 partial rotations and I want to know the size of each of them, right, I always take 360, which is 1 full rotation, and I can simply divide it by 3. And I get 120 degrees. Right, and then we can do the same thing for the next 2. I'll do these quickly, but if you want to pause the video here, kind of give them a try, and then you can check your work, right? So the first one here has 2 lines of symmetry. It has an order of rotational symmetry, again, of 2, and that means that its angle of rotational symmetry is 180 degrees. And then for this next one, it has a 1 line of symmetry. And because this point right here, if we try to rotate it, we find that it never gets back to looking the same until it goes through 1 full rotation. So since it doesn't get back until we get to the beginning, there's no such thing as an order of rotational symmetry of 1. So what we'd say is that there is none. There's no rotational symmetry, which means that there is no angle of rotational symmetry either. Okay. So how do we rotate a shape? How do we take these shapes and we rotate them? So let's take a look at this shape, this pentagon here, A, B, C, D, E. And if I wanted to rotate it clockwise, right, we have to know what direction that means. So maybe we do, maybe we don't know what order the numbers and the clocks go, but they start at the top at 12 and they go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then back to 12, right? So if we kind of count these numbers in the order they're going, what we see is that we rotate this way. We call this clockwise because that's the direction the numbers go on a clock. And then if we wanted to go the other direction, if we wanted to go back that way, we simply call that counterclockwise, right? Because that's the opposite direction from the numbers on a clock. Right, so if I'm looking at this shape right here and I want to rotate it clockwise, clockwise means I'm going to rotate it that way. And then it says about vertex E, because what that means is we have to have a spot, we have to have a point in which we are rotating our shape, right? Because something has to stay still, right? It's almost like I'm taking a pin and I'm putting it right here in corner E, and I'm making sure that E doesn't move, and then everything else is going to spin around that. So if I want to rotate these shapes, what I want to do is I want to move each of these lines 90 degrees. Well, here's my 90-degree angle here. So what I'm going to do is I'm going to put this right here on vertex E. And what I notice is that this side length here at E to D, right, is now being rotated 90 degrees. So if I take this and I move it up this way, right, there's my 90-degree rotation. Let me rotate that real quick. Okay. All right, and if I do the same thing for A to E, right? So I can do exactly that same thing for A to E. So I can take my corner and I can put it on A, right? Maybe. Oh, there we go. right? And again, I want to rotate that 90 degrees, right? I want to make sure I'm rotating it in the correct direction as well. So there's my original line segment, right, from E to A, right? But again, now what I want to do is I want to take this line segment that's right here, and we're going to rotate that 90 degrees this way. So now it's going over here. And then the same thing will happen for my other points as well, for my D to C and my E to B, and so on, right? So what we'll end up with a shape that looks like this, right? Where that point E won't change positions, right? E is still going to be here, but points A, B, C, and D will have moved, rotating around that point E. And usually the notation we use to denote something that's moved or to a new spot is we use this little apostrophe, A prime, B prime, C prime, D prime, right? To say that these are not the original points A, B, C, and D, but instead they are the new points A, B, C, and D. One thing to consider is, how do I rotate these lines or these points that aren't directly attached to E, right? A to E was fine because I just set up my angle and I rotate it, and E to D is fine because I just set up my angle and I rotated it, right? But what happens is when I'm looking at points that aren't necessarily right attached to E, it gets a little bit more tricky. So what I like to do is I like to break it down. I like to say, all right, well, here's my up-down piece of it, and here's my left-right piece of it. So let's say, for example, that from E to D was 2 units. I don't know how big the units are, so we'll just say it's 2 units. And then from D to C is only 1 unit, right? All I really have to do is, instead of trying to rotate C about point E, what I'll do is I'll rotate the directions. Instead of going down 2 units and to the left 1, right, and to get me from E to C, I'm going to take these directions and rotate those 90 degrees. So this down 2 units is going to become left 2 units, right? And this left 1 unit is going to become up 1 unit. And notice that when I rotate these 2 directions, over, down, and over, they go over and up. And where do I end up? I end up at my new point C. So my old point C gets rotated up to this new point C, right? So it can be easier to try to rotate the directions instead of the whole shape itself. All right, let's try another one. So I'll get you guys to try this one. Maybe pause the video right now, see if you can't get this one. And when you are done, we'll check our work. All right, so to save myself a little bit of time, what I'm going to do is I'm just going to take that shape and I'm going to clone it. So again, we are rotating counterclockwise. Remember that counterclockwise means we are going against the clock, so we're going that way. Point F is the point that's going to stay still, right? So this point F right here is the one that's not going to move, and we want to rotate 120 degrees, right? So if I want to make sure that I'm in the right spot there, so we can now line up my points from F to G with the new positions from F to G. Making sure that F doesn't actually move, right? So there we go. So I should have a new shape that looks something like this. Okay, so one last question here. What we can do is usually what ends up happening nicely is if I'm wanting to work in rotations of 90s, right, 90, 180, 270, right, I actually want to, or would be helpful to have a grid kind of like the one here, because these grids are set up in 90-degree segments, right, from my y-axis going up and my x-axis going to the right, we have this nice little 90 degrees. So all of these directions that I was talking about in the previous question are easy to find with this one. So for example, if I wanted to rotate this shape right here, shape ABCD, 90 degrees clockwise, I don't have to kind of guess, right? I don't have to say, oh, it looks like this or it looks like that, because I have these nice little grids that are set up at 90 degrees. So from A to B, I know is going to the left, 2 of these little squares. So if I take that and I rotate it 90 degrees, where am I going to be? Well, I'm going to be going up 2 of these little squares, right? And then same thing from A to D. So from A to D goes up 3 of these squares. So if I take that direction up and I rotate it 90 degrees, I find that I'm going right 3 of these squares. So there's my new point D and my new point B. And again, C, because this shape was a rectangle, we can kind of see where it's going to be. We know it's going to be here. But again, let's take the time to see why that is. So again, to get from point A to point C, follow directions, right? So I have to go over 2, and then I have to go up 3. Right? So if I take each of these individual directions and I rotate them 90 degrees, this over 2 becomes up 2, and then my up 3 becomes right 3, and I see that I have my new point C. So now that I have my points, I can put them right there. All right, so again, I'm going to let you guys try the next two. So try them on your own real quick, and then I will go through them with you guys. All right, so let's do it. So 180 degrees clockwise. Again, A is going to stand still. So we're going to take all of these directions and we're going to rotate them 180. So this A to D is going up. So from A to my new D is going to go down. From A to B goes left. So A to my new B goes right. And then again, my new C, we would follow both directions, down and, left and up, and they would become down and right. And then finally 270 degrees. So there's my 90, my 180, my 270. And we'll do one more color here. So my left going 270 degrees now goes down. My up going 270 degrees now goes left. And then finally point C is right here. Okay, so there are my two new shapes. So we have B prime, C prime, and D prime. And in fact, maybe I'll use double prime to indicate that these are not the same as the other ones. And then we have B triple prime, and C triple prime, and D triple prime. Okay, and that is it for today's video. Yeah, I'll see you guys in the next one.